Well, good morning, good afternoon, good evening, I suppose good night to wherever you may be across our lovely world. Thanks for joining us live here today for Serverless Office Hours. And we are streaming on the one and only AWS Twitch channel. I'm Julian Wood. I'm a developer advocate here for Serverless at AWS, and I'm super happy to be joined by two proper experts, let me tell you. I'm going to go to Anton first because Anton is a recurring guest because he just knows more about AWS Serverless than probably most of the planet put together. So, Anton, for people who don't know you, how come you're doing serverless on AWS? I ask yet again because it's so cool to have you back.
Hey everyone, good to hear from you again. I'm Anton, Principal Solutions Architect here at Serverless. I've been doing this for, Julian, you wouldn't believe it, I'm getting close to 4 years, right? The time really flies by when you enjoy what you do. So yeah, I'm based in Austin, Texas, and I'm covering a lot of fun serverless technologies like Lambda, Event-Bridge, Step Functions, and many more.
Cool, excellent. And today is a proper nerdy deep dive, I promise you. And so, let alone Anton's credentials and being such an awesome expert, we have Rajesh Kumar Pandey, who is a principal engineer on Lambda. For people who don't quite know what a principal engineer is, this is one of the people who literally builds Lambda. So yeah, Rajesh, how are you today?
I'm great. How are you guys? Hi,
Excellent.
I'm Rajesh Pandey. I'm a principal engineer with AWS Lambda. I've been with Amazon for about 12 years now.
12 years.
And
So I mean, in Amazon years, that must be like 150.
yeah, and yeah, I like joined fresh from college, I'd say, and then I've been with different parts of Lambda, but I've been building this like large scale distributed systems from maybe like last 7 8 years, and then before that I was a user. Now last 8 years I've been spending time building these things behind the scenes. So I'm great to be here, excited to be here.
Well, thank you. Well, and everybody else who's joining us, please remember we are live. We love your questions. We love your comments about Lambda, which we're specifically talking about today, but also serverless in general. So also, please tell us where you're from. We are actually always amazed and enthused about how global our serverless audience is. We've got the first telling us, Akhil Rawat, hello to you too as well. But yeah, please tell us, where you're from. It's always nice to find out where people are listening from. Now, the title of this live stream today is Billions of Lambda Invocations. Sort of like that. Now, Lambda is a huge kind of service. It's literally one of my favorite services. I think it's incredible. It's one of the reasons I got into serverless. So obviously, there's a lot of information about how Lambda runs that is super useful if you're running your own, multi-tenant, maybe SaaS applications or running your own kind of thing. So, over to you, Anton. We are talking about Lambda and how it works under the hood, but why is that applicable to people who may be watching today?
Well, one of the best things about Lambda, and I'm with the same boat as you, Julian, right? It's serverless nature, right? So I'm gonna be 45 this year, right? That's a big secret that not a lot of people knows, and I've been doing this in the industry for over 20 years. I've seen a lot of iterations of different ways to build stuff in cloud, right? So I've seen how to build it with bare metal servers, virtual machines, containers, etc. The fun thing about Lambda is, as an application builder, I don't really care about any of the underlying architecture, right? I just write my code, and AWS, people like Rajesh, help to make it sure that it just works for me, right? So my focus is shifted, right? I no longer need to maintain a huge operations team, but I can focus much more on actually developing the code. So, the biggest secret of serverless is there are tons of servers, probably tens of thousands, if not more servers under the hood. But it's not me as a consumer who needs to maintain them, right? It's AWS and Rajesh personally, right?
Yeah, yeah, yeah. Literally, there are like tens and hundreds and thousands of servers behind serverless. So it's serverless for like our customers and serverful for us, and we do all those things that you said. So it's the abstraction uh, that we pride ourselves in, is like when we give that abstraction to our customers, so they can just literally, when we say like fire and forget. So customers can fire and forget, and then behind the scene we do fire, observe, monitor, retry, back pressure, and all those things. So behind that fire and forget, all these things that happen, and we leave, like we do
Yeah.
that for our customers.
Has Rajesh just let out the dirty secret that there actually are servers in serverless? Oh, imagine that.
Yeah.
There are lots, yeah. So
Yeah.
obviously, there are obviously loads of servers behind serverless, but I've always sort of likened it to like wireless. When you consume a wireless, on your laptop and you're consuming wireless, there's no wires that you're consuming, but there's a lot of wires that are connecting all the switches and infrastructure in the background.
Right.
So it's a similar kind of concept. But obviously, Lambda is huge. I mean, what we had some stats, which I will show in the blog post. I mean, we talk about, I've got the wrong blog post, silly for me, but we talk about, 1.5 million, slight different, but that sort of million monthly active customers and tens of trillions of invocations that are processed, with security and reliability built in. So, one of the questions people may think is, hang on, I'm running a business, or my Lambda functions are going to be running with other kind of customers. There's a security concern for this as well. But in terms of performance, there's also this, crazy noisy neighbor kind of thing. How do we think about first of all, how Lambda handles that, and then what customers should sort of take away from thinking if they're building their own applications?
So, well, let me start with defining what a noisy neighbor is, right?
Sounds
Because
good.
I think this is a pretty interesting concept, right? The name is kind of self-explanatory. If you ever lived in an apartment building, right, you know what a noisy neighbor is, right? It's essentially a neighbor that other neighbors don't really fond of, right? Because it makes everyone's life harder, right? So in cloud compute, a noisy neighbor, it's one of the tenants or users of your system that's unpredictably, right, maybe without any malicious intent, right, but suddenly starts to consume an excessive amount of your system resources, right? Every single system has its boundaries, right? So, that the system, the way you built it, can process, let's say, arbitrary number, a particular number of requests. And you hope that all of your users, all of your tenants will kind of share that capacity amongst them. And then you have that noisy neighbor who suddenly says, well, you know what? I need 70% of that capacity, and I don't really care about the remaining tenants or users of that system. So that's kind of the noisy neighbor, right? Now, noisy neighbor problem, it's not a new thing, right? It's, SaaS exists for many years, multi-tenancy exists for many years, right? So noisy problem exists for many years. Sometimes it's less of a concern, right? Sometimes it's more of a concern, right? So, in order to address noisy neighbors, first of all, you need to acknowledge that you have that problem, right? Because not every single system will have that problem. And then my take is you need to properly deep into where that problem is coming from, right? Is this malicious activity, right? Or maybe it's actually proper, intended usage, right? It's just some of your users are smaller companies. Some of your users are larger organizations, right? So how do you design your system in a way that it will be able to provide excellent quality of service for all of these scenarios?
Yeah, so I mean, and noisy neighbor has been around forever. I mean, even if you're talking, building, shared databases on a SQL cluster that, you had one database that was doing analytics queries, you've always got competing interests for different kind of things. And that's what makes the cloud amazing. You do have this elasticity, but then you do need to deal with sort of not competing workloads and understanding about that. So yeah, how do customers then, start maybe handling these multi-tenant workloads?
So just to add, I was explaining this concept to someone who just joined, and I think I used an example of chocolates that you put outside your house during Halloween, and one kid comes and grabs all the chocolates. There is nothing left for other kids to grab, right? So that kind of when you have a shared resource pool, and then if one kid comes and takes all the chocolate, there is nothing. So that's kind of and is an example that I use someone to explain what a noisy neighbor is.
I would be annoyed if somebody stole my chocolate, so I know exactly what you mean.
Yeah. And one of the tenets that AWS follows, and that's I've been following, and it is something that I learned from one of the distinguished engineers back in 2015 when we were talking about building about talking and scaling it. DynamoDB is we want to build multi-tenant systems, but we want to give single tenant experience to our customers. So that in itself, what is saying is like there is a shared pool of things that we want to share, but we want to build a service in such a way that like there's a isolation built between like customers in such a way that like roles resources are shared and they never get this experience of like they are sharing that pool. So that tenet is what we follow. And again, that tenet has its own tension, right? Like when you have a shared resources, how do you when you are in this kind of an environment, and this is something that like all the big organizations, those when we are talking about like distributed systems, how do we build these kind of systems? And that's inherent. There is an easy way for us to build a system where like a single customer deals with a single thing, but like how do you manage the performance and the benefits of cloud? This is what you get from building these kind of things, where like you share a shared set of resources with a like a bunch of customers. And when you manifest into problems like noisy neighbor. And there are like millions of ways to deal with it, and like in the sense of like we dealing with like in Lambda, we have talked about a bunch of things that we do behind the scene. There is always a trade-off. It's not like you can't end up like building a one set of like box for a single customer. So how do you build those trade-offs? How we started, like our journey was with like, okay, start with a simple queue which is shared across customers, and then we introduced this like a shared chocolate box. And then like, oh, some kid came in and like took a lot more than what they were supposed to. And then, oh, maybe we can have two boxes, two bowls of chocolates. So bunch of things that went into, and it's a like a learning process. We iterate over it, and um, and got to solve like some of the interesting problems that we see here.
Excellent.
There's a
Anton,
very
did you have some diagrams you wanted to bring up? I just wanted to ask.
oh
If
yeah,
if you don't,
absolutely.
that's fine. But I just
Absolutely. I can show some stuff as we talk, right? But there was like really good comment in the chat. First step to addressing a problem is acknowledging you have a problem,
yeah.
right?
Thank you, Vector Hacker.
This is like right on spot, right? I'm gonna write it on my wall, right?
Yeah.
Now, like we're engineers, right? I would imagine the audience also have some technical engineering, some background in that, right? You can solve a problem in many different ways, right? But it's crucially important to find a solution that is most efficient to the problem at hand with some future considerations, right? Once you acknowledge the problem, there might be different ways to solve it, right? Don't always pick the most sophisticated, the most complex solution, right? The most advanced solution will bring in the most advanced complexity, right? And maybe you're just not there yet. To give you an example, right? Let's use a very common example of a shared resource, SQSQ, okay? Maybe you've built a solution that is using a single SQSQ, okay? You know what? SQS is probably one of our most scalable, like I'm not aware of anything like that can scale as much as SQS. It's an amazing service, right? It can handle, if you look at the quotas page for SQS, there is something like there that says like virtually unlimited number of messages, right? Like imagine seeing that kind of statement from AWS, where we're very proud of declaring our quotas because we want to keep the highest level of quality of service, right? A single SQSQ can give you a lot of capacity for multi-tenant applications, right? Maybe in your specific application, you're not at a point yet where you need to, consider that as a problem, right? But once you do get to a point where this is a problem, this is where great monitoring comes in place, right? And this is where you can decide what are the next steps that you're going to take, right? So, to show some slides, right, to inject some interesting data into here, right, because we're starting to kind of think about, starting to talk about how this would look like, right? Now, I'm not going to show all the, 90 slides I have in this deck, right? So, the noisy neighbor problem, right? This is the utopia, right? This is where you want your applications to be, right? You want your tenants to consume something like 70, maybe 80% of the capacity, and you got some spare in case, in case of growth, right? But in reality, right? The expectation is your noisy tenant, this T10 here, right? Once it arrives, you will have some perpetual auto scaling, right? I have a noisy neighbor. Well, my capacity can scale up perpetually without any constraint. Well, this is not the way it works in real world, right? In the real world, even with serverless, you always have some sort of limited capacity, right? For example, with Lambda, you have your account concurrency limit. That's your concurrency quota, right? We can raise it if you need to, right? But this is something you have set up for your account. So in reality, when that noisy neighbor arrives, right, all the other tenants will gradually get less capacity. Now, to illustrate that, right, I've created a series of prototypes, right? And essentially, this is what I wanted to measure, right? So it's a very, very simple architecture, right? Multiple tenants, right? And there's API gateway with the queue that receives those messages, right? And there's a single processor. Now, what does that processor do? It sleeps for 300 milliseconds. It doesn't really do a lot, right? Because I wanted to simulate some work, right? But I'm measuring end-to-end processing time. Now, this is a very simple kind of architecture, right? In my tests, okay, I'm running 20 tenants, right? So here you can see I'm simulating 20 tenants, and all of them roughly have the same number of requests per second, roughly, okay? I call it my peace and quiet zone, okay? But then I'm configuring my tenant number 20 to be much more noisy, okay? This is my noisy neighbor zone. Now, let's skip some slides and let's see the result of that, right? So here you can see a CloudWatch screenshot. That's 20 tenants with only one of them being noisy. Okay, what you see on this chart, for example, is every single tenant is affected, right? And remember, the processing time is supposed to be around 300 milliseconds, but you can see that it starts to spike the moment noisy neighbor appears. It goes to 50 seconds, and this test is just running for about 10 minutes. If I keep it running for more than 10 minutes, it will continue to rise forever, right? Until that noisy neighbor becomes quiet again, okay? So you can see here this, right, this point, 23, 25, 57, right? I did not actually run it middle of the night. It's the time zones, right? Trust me, right? But at this point, this is where the noisy neighbor, is no longer noisy, right? And you can see that the traffic is starting to go down until it goes down to, the original value. But until that neighbor become excessively noisy, right? My processing was kind of fair for every single tenant, right? And that's where noisy neighbor kind of started to affect everyone, right? This is the point, right, where you start thinking, okay, I need to implement some techniques that will actually reduce what's called, there are several official terms, blast radius, impact radius, right, ratio, or whatever, right? Essentially, it's possible you will have a noisy neighbor, right? It's definitely possible. You cannot predict you will never have a noisy neighbor. But how do you actually address that, right? How do you, for example, implement some throttling on API gateway, right? Or alternatively, how do you actually architect your distributed service in a way that knows how to accommodate noisy neighbors, right? And this is where Lambda did a lot of great work.
So yeah, so this is interesting. So this is showing that just a single noisy neighbor basically messes it up for everybody else.
Mm-hmm.
I mean, that's a simple, you've got, 19 all fine, and this average is just nicely over this curve. And I don't 100% believe you. I'm sure you were running this at midnight, but anyway, I know you like that, Anton.
Let's talk about midnight. So this is 23, right? This is 10 minutes before midnight. You have a noisy neighbor that turns on music, and now every single neighbor is awake, right? Everyone is affected by their music, right? This is the reality of it, right? 10 minutes later, they shut that music down because they're just running an experiment, right? And all the other neighbors or tenants are going to sleep again gradually over the course of the next few minutes. But the moment that music is super loud playing on the speakers, right, in a shared environment, everyone is affected. That's kind of the idea.
Okay, so what do you do then? Obviously you can go and knock on the neighbor's door and tell them to turn the music down.
Just to add to to like what like Anton was saying, that like and sometimes like these noisy neighbors, like some customers are like or someone like that one tenant knows that like I'm playing music very loud. Sometimes their window is broken and they don't know that there's windows broken and their noise is getting out, right? Like, so it's always that, like, because some customers are noisy or someone is noisy but they don't know. Sometimes it's intentional, sometimes it's unintentional, sometimes like the environmental factors are around them in such a way they appear to be. So like there is always like someone has a genuine need to do something. For, let's say, they are preparing for like an event, like a Black Friday event, and then the retail website is going to get a huge spike, like maybe Nike or someone, and they are just like testing their system out. So they may appear as a noisy customer for a service, but what actually they were trying to do is like just preparing themselves up. So they have to have that. So like you need to know like how you qualify like a customer or like in a partner or a tenant as a noisy, and like what are the impacts. So just wanted to add that, like, so there are like different layers of like noisy customers and noisy tenants.
Yeah, that's a really good point, because you could obviously have a noisy neighbor issue where it's sort of, deliberate, where someone's taken down the system, but it could just be, some, misconfigured batch size or misconfigured payload or something like that, that you really just have no idea, and this is unexpected. The customer, if even in a SaaS thing, customer may not even know or have any concept that this is something's going on.
I'm gonna throw another use case there, right? So yeah, some of them are unintentional, like maybe maliciously noisy, right? Some of them are unintentionally noisy, right? Because like a bug in the code, right? And then now they're cycling something, there's some recursion in the code, right? But ideally, you do want your customers to consume your system as much as possible, right? Some use cases are, in some scenarios, you do have customers that occasionally, right, spike their traffic by, let's say, X hundred, right? Because this is their legitimate use case, right? Imagine a company that does some document processing, and several times a day they're dropping 500,000 documents into S3, and now they need to process that as soon as possible. Okay, so that's your noisy neighbors, right? Other smaller companies, they might drop like 50 or 100 documents. This one, 500,000 documents, right? And you actually want more of these customers who are processing a lot of data through your system, because this is, realistically how you make money with your product, right? But you also need to make sure that your product can accommodate that.
Right.
Yeah. You want to talk about different strategies?
Yeah, this looks terrible. How do I fix it? That's certainly different strategies. But actually, I also forgot to say, Michael Walters, thank you very much for joining us again via Twitch. And Peter Smith, good friend of Serverless Office Hours from New Zealand. I worked out it's 23 minutes past 6. So you joined us at 6 a.m. So that's very keen of you, for the other Southern Hemisphere folks, to also say hi. So lovely to hear from you. And cheese ball for you. Thanks for streaming about this. Well, pleasure.
Yeah.
Yes.
And just one thing is like and like as an AWS and then as an Amazon is like we always want to ensure that we build systems and design systems in such a way that like these issues are like mitigated, and we also want to make sure that like we provide tools and like what like Anton was talking about, like observability and like those sorts of tools, so that like customers also understand their behavior and like they can take actions. So there are like both layers of protections. We'll talk about like some of the techniques that we have done, but like there are always like tools and services, and these things are available to our customers also, so they can understand their behavior. They can look into this. Like sometimes it's a code bug which is causing this. They don't want it. Like recently, like we improved, we launched a feature around recursive protection, where like some customers were unaware of that, like they were using the same queue to process Lambda and then writing back the same queue. So it was creating those like, so we always like look for those kind of things where there's like unintentional behaviors. And we do provide a lot of like tools and like metrics and that customers can use to understand their behavior.
And it's important, like in context of Lambda, right? We're showing this chart that shows that the number growth, right? It's important to understand why is it happening, right?
Yeah. Right.
Because even with Lambda, you have a limit on the concurrency in your account, right? So essentially, that limit can be higher, that limit can be lower, but there is some limit on the concurrency in your account. When your noisy neighbor starts to arrive, right, they will start the concurrency, right? It will gradually start to grow, right? But at some point, you will start getting throttled once you hit that concurrency limit, okay? And this is where, this prolonged processing might manifest itself, right? Because you're just consuming all the capacity, all the concurrency you have in your account, right? And your options are
Yeah.
to either request for more concurrency or fix the problem.
Yeah, and like sometimes it could happen like a customer in themselves might be competing for the resource. So like there is like concept like result concurrency. If you have multiple functions that account concurrency is shared across functions. So you could actually be impacting yourself. Like you have three functions attached to like two different queues, but you are all them belong to the same queue. So your own one function can consume a lot of concurrency, and you are left with like nothing for the others, right? Like so it doesn't have to be like an inter-customer or like different customers, your own account. So like it's important to understand these behaviors so you yourself can like better use of these capacities that are available.
Yeah, and so there are two parts to that concurrency, which I love explaining to people. That one of it is fairness, and but as you said, even within your own accounts, you could have 1,000 functions. You want to share concurrency within your own accounts, and also for the Lambda service to keep running for millions of customers. But also it's a cost control mechanism and a performance control mechanism for yourself as well, because if you write something in your own code, or you have something recursive or something that goes crazy, Lambda's going to scale up as much as you want. So that's the control that you can at least create some bounds for what is expected behavior with your application, so it doesn't go too nuts.
Yeah, I think the big question we need to start answering is, how do you actually solve this, right?
Sounds good.
To reiterate again is, this picture looks, this picture tells an interesting story, right? But once again, to reiterate, it doesn't mean everyone gets to that story, right? This is huge scale. This is a noisy neighbor at huge scale. So we're going to be talking about solutions, but it's critical to understand when you need this solution and which solution do you use, right? It's definitely critical, because out of the box, serverless kind of solves a lot of these problems for you, right? The solutions that you're going to see here, a lot of that is solved by default. The general approach is like, well, two things, right? First, what you can do using services that are fronting your workload, right? So for example, if you're using API gateway, it has an excellent mechanism for throttling requests, right? You can define how many requests per second you want to allow for each of the clients, right? So it's a relatively simple way of actually protecting your, what's hidden behind your API gateway, right? By using that feature, you can have each tenant adhering to their own RPS, request per second quota, right? This way, you know that API gateway is protecting you, right? And whatever is behind API gateway, right? It's not necessarily going to be bombarded with requests, right? Because API gateway is going to kind of accommodate that for you, right? But at some point, you want to say that, what? I do want my architecture to be able to handle these kinds of workloads, right? Spiky workloads, noisy neighbors, right? Yes, I want some protection from the API gateway, but I want my workload to be able to handle that, because I want to advertise that, hey, I'm resilient to that, right? You want to bring those like X100 traffic spies, bring it on. I can handle it, right? So Lambda scaling, Lambda gives you for each function 1,000 execution environments every 10 seconds. For each function, can you imagine how spiky that can be, right? So you might want to have something like that in your application as well. And kind of the keyword there is cell architectures and sharding, right? So we'll talk mostly about sharding, right? So a common approach to protect your workloads from this noisy neighbor problem is to shard the workload, okay? There are different ways of sharding, right? Sharding essentially means you're taking some part, right, some segment, and you're isolating that to a separate shard. Now, this can be different things, right? You can think of sharding, for example, in your workload. I'm going to create a new account, let's say per 100 tenants, okay? Because now I know that a single account can host up to 100 tenants of mine, right? That's going to be my sharding strategy, Okay, you can do it differently. You don't have to create separate accounts. You can say, you know what, I'm going to be using downstream. I'll be using a separate Lambda function per tenant, right? Because each Lambda function comes with its own reserve concurrency, provision concurrency. You can configure that, but you're still capped at the overall concurrency level in that account. So there are different sharding techniques, right? Some of them are more on the resource level, some on others level, right? And this is essentially what our blog is talking about. Rajesh, you want to talk about sharding? Because that's your baby.
Yeah. I think just to add to like what you were saying, like when you uh, like I'm just taking like a account boundary as a like a single customer boundary and like single customer defined, right? So one of the challenges that we have, like how do we like load balance these like customers across our servers so that uh like customers are like getting the service that they are expecting, right? Like so when you talk about like 1,000 concurrency, like you get instant 1,000 concurrency. So Lambda has this property of like you can burst to like a higher scale, and it's very elastic in nature. And that elasticity is achieved through like how do we distribute and load balance customers across our servers so that like everyone is getting a capacity and they're getting their like a fair share of like the compute capacity so they can like actually work on it. So one of the things that we did like early on is like I think like and a lot of companies do that is around like how do you distribute your customers across your server capacity. So you have a finite server capacity, and now you have to find a way to like map those set of customers onto those set of servers. Right. So one of the very early on, we started with like a single queue. I think we talked about like briefly about it, and then we went into like multiple queues. But like how now, if you think of queues as a servers, then like you have to find a way to like map those customers onto those set of queues. And then and as a principal principle, right? Like if there are n servers and then you have m customers, then m has to map to n. So for that, like we used like consistent hash as a way. So created a range of we created a hash range, divided and mapped a separate queue onto those look hash ranges. And every time a customer comes, we hash that to a hash function and then map it onto like that shard of hash which is attached to a queue. So this is basically what we did behind the scene, and that's how like it's and again not very specific to Lambda, but it is like in general like you have to shard customer traffic where like you have m set of like a defined set of capacity, and there are like a n like which is more than the number of servers that are available for the customers. You need a way for you to use some sort of like these kind of mapping where you can fetch. So we divided that hash range, divided them into like number of queues, those hash ranges, and then map the customers onto that. And we specifically use consistent hashing because it has this. If you think about like a simple function, if 5 customers modulo 4 servers, then there's like 2 customers getting mapped onto like one specific server. But now you need to add a host to it, so you 5 modulo 5. But you have to now move customers. So the consistent hashing has this property where like you minimize the movement of customers across the servers, and because every queue is behind the scene is attached to a resource which is polling and then like invoking your Lambda functions on your behalf. So we wanted to minimize that. So that is basically the starting on like how do you load balance customers across your servers or queues behind the scene.
Yeah. So I've implemented something very similar in my experiments, right? Essentially, I called it simple sharding, right? And the idea is you have those queues or processors or essentially the unit, right, that has a constrained capacity, right? And you can assign multiple tenants, right, to those units, right? It can be random, it can be based on hash, it can be on many factors, right? But essentially, the goal here is how do you minimize the impact, right? Potential impact, right? So this is the experiment I've implemented. Okay, and here, if you remember the previous architecture, this one is a little bit more complex, right? So here, I'm essentially saying that I will have multiple shards, right? Which is just a queue and a processor function, right? And I will dispatch those messages. This is a simple shard, completely randomly, right? So essentially, each one of those 3 shards, right, it will get roughly the same number of messages. So I'm distributing that workload, well, not randomly, sorry, based on the tenant, right? Based on the tenant ID here. So the dispatcher knows which shard belongs to which tenant, right? And all the messages from a particular tenant goes to a shard that that tenant processes, okay? Now, anyone wants to guess, how those like clickbait articles, right? We implemented this solution. You would never believe what happened next, right? Anyone wants to guess what happened next, right? Because the next thing I'm going to show is the CloudWatch diagram that we got as a result, that I got as a result.
Well, I think you're going to have 1/3 being busy and 2. Oh, yeah. Not quite what I thought, but.
You're right. You're absolutely right. You're not seeing about 80.
Yes.
Yep.
There we go.
About 80% of tenants, right, are right here, right? They're still at the very bottom there. You only have 3 tenants affected, okay? Because those were the tenants that used the same shard, right? All the other tenants, they were using unaffected shards, right? And that's why you can barely see them on this diagram, right? They're still in this less than a second range, while these tenants, you have a noisy neighbor in that specific shard, right? I ran this test a little bit longer, so you can see it's getting to a little over 2 minutes now at the peak, right? But once that noisy neighbor subsides, right, when it's no longer noisy, you can see the traffic drop pretty dramatically because the shard has its full capacity to process the backlog, right? So this is the power of just a simple sharding, right? Essentially take that constrained resource and scale it horizontally, add a few instances of it and declare them as shards, right? So this is a very simple calculation, right? So the number of affected tenants would be your total number of tenants divided by the number of processors. So in my experience, I had 20 tenants and 8 processors, 3, which means only 15% of tenants were affected, right? Instead of 100 tenants, which we saw like 10 minutes ago, right? So this is already a pretty decent improvement, right? By upgrading the architecture of your applications, right? But can we do better?
And so that is that's consistent hashing. Each customer ID which you store in a table goes to a particular processor.
Mm-hmm. Mm-hmm.
Okay.
Yeah, with consistent hashing, it's a pretty simple mechanism, right? You essentially say that I'm going to create 10 shards. I know the rough capacity of my shard, right? And I'm going to assign, up to, let's say, 100 tenants to that shard. Whatever I have tenant 101, 102, 103, I'm just going to create a new shard. And this way you scale those shards, right? This way, if one of those tenants becomes noisy, only one shard is affected, not everything, right? So essentially you're isolating that blast radius or impact radius, right? And the more shards you have, right, obviously, the smaller that impact is going to be.
Yeah.
Yeah, and just to slightly caveat is like this thing you don't need even the consistent shard. You can just do a modulo operation as your hash function, and then you will be able to achieve this. Like what reduction is showing is like you can achieve it. Where consistent hashing comes into and plays, it's like when you change the denominator, and let's say you want to achieve a higher factor without making or migrating your customers. So what function he was showing in that graph, if you add one more queue, what will happen? Like whether you rehash all set of customers, so maybe there is this goes to like 20% of the customers getting impacted. But if you use those consistent hashing mechanism, then maybe it will be like 16% and not like higher. So I think if you are managed into like those set of queues, I think this is like absolutely, and this may be enough for a lot of customers, like a lot of service providers. You may never see any issues. Like this only manifests when you are like operating at like a very high scale. Even like a 1% of customers has like that high of a throughput, which can impact a lot of set of customers which are hashed out on the same shard.
Okay, so it's the nuance on that whether you maintain the sort of customer shard mapping in a table or something, or you just do a random, you do consistent hashing, but it's just random. So say based on a customer ID or that kind of thing, do some hashing modulo as you're mentioning, and it goes across. The nuance for this is, okay, what happens when you then add processes? Do you want to then still maintain the place where the customers were going, or where the new customers maybe go to new processes, and so that's just how you manage that. So you could
Yeah.
go simple and just spray them randomly across, but always maintain that they go to the same place.
Yeah, like Anton would not like it. Like if he has achieved a 15% reduction, like from 100% to 15%, he won't like to go it up again back to like 50%, right? Like, so he needs to have that kind of like, I've improved my system state. I want to keep it improving. And I think that is what he'll show us how to do it next.
Okay.
Yeah. And like to add to that, right? There are different strategies you can take, right? You can randomly fan out across all the shards, all the queues, right? You can do that. This way, you're spreading the impact, right? But essentially affecting every single shard, right? So if your goal is to spread the impact, random works just fine, right? If your goal is to isolate the impact, this is where you might use more of a consistent sharding, right? So essentially, a particular source always goes to a particular shard. And yes, there are like resharding strategies, right? That's like the next level of that. Okay. So yeah, this is essentially what you will see in the blog. I will share the link at the end that me and Rajesh wrote, right? But you know, as always with AWS, we wanted to provide something significantly better, right? Something much more robust that can handle the scale of Lambda, right? To remind you, tens of trillions of requests. Okay, that's like that number is not even easy to write, right? It's a huge number. Okay, so the approach that we evaluated, right, and what we describe in the blog is shuffle sharding, right? So shuffle sharding, it's an interesting technique, right? It's based on math. Okay, now remember previously you had tenants assigned to a particular processor. So each tenant was assigned to a particular processor. And I'm using processor as a generic concept here, right? To a specific shard, right? Now, what happens if you take a tenant and instead of assigning it to one shard, you assign it to two shards? Okay, that's kind of the idea. And then each one of your tenants will be assigned to more than one shard. It can be two shards, it can be three shards, but essentially more than one, right? So it's kind of reversed approach, right? Not like, you know, one processor can process multiple tenants. No, one tenant can be processed by multiple processors, right? So if we're going to gray out the rest, right? Now imagine this is your state, right? You have tenant one, which is a noisy neighbor, and you have tenant four, which is an affected tenant, okay? Now they share that second shard, the second processor, okay? Which means, right, you have two shards here, right? Shard one and shard, let's call it four, okay? Two different shards, right? Which means that because tenant one is noisy, the first shard is super busy, the second shard is super busy, but the third shard, it's not really busy, right? It's pretty low level of busyness, right? How you can measure that? If your shard maps to SQS, maybe backlog. If your shards maps to compute, maybe CPU usage. You always have some metric to understand the busyness of a particular shard, right? So what can we do in this scenario, right? Tenant 4 can be pretty smart and say, you know what? I'm getting at the moment pretty horrible service from that second shard. I'm going to stop using it. I'll just use the one that is not as busy, right? And this one, the experience of this tenant is no longer affected by a noisy neighbor, right? So this dynamic rebalancing, right, is essentially what helps tenants to achieve the highest quality of service, right? Rajesh, you want to talk about the math behind the scenes?
Yeah, basically, and again, like I was talking about like the modulo, right? Like it's a very simple modulo. Now you add onto what basically you have to do. Like if you take a simple hash function, you have to do is like pass the same customers onto and get like two set of hashes. Again, like the hashes is saying that the range of hash is attached to like a processor behind the scene or a queue in this case. And when you hash those customers onto two sets of queue, you check both the queues and see like the very simple technique. Like again, I know like math looks like it's a very complex system where we are like trying to find out like two tenants on okay, one is busy and one is not. And busyness can can be as simple as checked as this, right? I go and hash my customers onto like those like hashes and find okay attached queues and check the queue length. Basically, that is your way to check whether the customer is busy or not. If a queue has let's say 1 million messages into it, and again, resource can be a queue, could be a DynamoDB key, it could be like a CPU process, a code itself, right? Like, so if you go and check that, okay, this queue has like 1 million messages or there are many writes happening at the same time, maybe I go and try out in the other queue that I is also allocated to me. So you take both of those two queues and check, okay, whichever queue has the minimum depth at that time, you has that customer. And it works wonders. Actually, all the like a very similar techniques has been used in like load balancers. If you see like those load balancers, those are like milliseconds, like a routing which they do this similar like best of two kind of a thing. So best of two is a very simple way to like implement this whole like math that like Anton is explaining. So it doesn't have to be like very fancy. And again, there's like an N processor and then like NC2 problem that we solve or NCM problem that we solve. And then there are multiple combinations that happen. So you could do that. The beauty of like what like Anton was showing is that like now the probability of you getting into a noisy customer reduces or like you seeing an impact with it, right? Like now, if you increase the number of tenants, then like if you have, let's say, I'm just picking up a number, it's like 100, and then like you're mapping onto like three queues. So 1/100 into 1/100 into 1/100 is the probability of you getting to like a noisy customers on your own. So like 1 into 10 to the power 6 that reduces. And again, I'm talking about like 100 servers, and then like services have much more bigger service behind the scenes. So this probability reduces to like a much lower than that.
So imagine, right, the system, right, this shuffle sharding, dynamically assigning tenants to shards system, right? Whenever you have a new tenant, it is dynamically assigned to several shards or queues or whatever, right? The problem will be manifested when you have this. When you have two tenants, and by the power of random, they were accidentally assigned to exactly the same two shards, right? This is where tenant 1 will definitely affect tenant 6, and there is no way for tenant 6 to accommodate that, right? Because it's using exactly the same shard. So, and this is where math comes in. What's the probability of this happening? Bear with me. I'm going to show you the most boring, but also the most exciting slide in this whole presentation. This is math, okay? Just to show you some numbers, right? The top one is number of processors or shards, right? And then you have the shard size, right? Essentially, how many shards each tenant connects to. And I'm not using super high numbers, like 1 or 2 or 3. Then you have the total number of combinations, and then interesting numbers, right? So let's take a look at this one, right? Because this one is most realistic. Let's say I have 50 shards. It's not such a huge number, 50 shards, okay? And each one of my tenants is assigned to 3 shards only, right? So to be specific, I have 50 queues, and each tenant can use any random 3 out of those 50 queues. The total number of combinations here is getting close to 20K, okay? Which means the probability of 2 tenants using exactly the same shard is this, 0.5%, okay? 10 minutes ago, we were at 15%. Okay, now we're at 0.5%. 2 tenants, not multiple tenants, just 2. The probability of 3 tenants using exactly the same shard and 4 tenants using exactly the same shard. Well, you can see the numbers here, right? The more tenants and more shards you have, essentially, as the system continues to scale, right, the probability is dropping drastically, right? That's the power of combinations that you have here, right? Now imagine you increase 50 to 60, all those numbers going to drop significantly, right? Just by adding 10 more shards, right? Or 10 more queues, right? Scaling your sharding horizontally. That's where the power of shuffle sharding comes in place. We have this article published by Route 53. We have the link in the blog, right? So they're talking about how they do it, right? They have 2048, right? This is the size of the number of their shards, right? And this number, we then assign every customer domain to a shuffle shard of 4 virtual name servers. This gives them 730 billion possible shuffle shards, right? You can imagine the probability of something going south, right? With such a huge number of possible shuffle shards, right? So this was published by Route 53, and towards the end, we're also going to show, we'll follow up with some links as well.
Yeah, I mean, what I like about this approach is, in a way, the simplicity of it. I mean, the maths is impressive, and the percentages decrease. But starting from the fact of, if you are assigned to 3 processors, and all you do is check which processor is got the lowest queue, or the highest bandwidth, or the most CPU available, or the least amount of memory in use, whatever metric, and you just query all 3 of them, and then pick either the highest or the lowest one, which corresponds to it, and then use that one. I mean, that's literally the thought process that goes behind it. And to think how you can amazingly use the shuffle sharding behind it with all this, amazing complexity, and all your tenants need to do is just query 3 kind of things and say, what's my lowest latency? I'll use that one. And you can take advantage of this.
Exactly.
It's amazing. It's really amazing.
This is exactly what I'm doing in my last demo, right? In my last experiment, right? So you can probably see, right, what I've mentioned in the beginning, right? Depending on your scale, you need to pick the solution that works for you, right? This one, even visually, it's the most complex one, right? But you've seen the benefits of it. So it doesn't mean that you absolutely have to implement this one, right? You can go with a simpler approach, right? But in this specifically, I'm adding Event Bridge Scheduler that runs my refresher function every couple of minutes, every few minutes, right? You can control the kind of the threshold. It's completely up to you. What that refresher will do, it will get the backlog size from all of the queues and store it in a dynamo, right? So my dispatcher Lambda will know which queues are the busiest at the moment, right? And it will route those messages automatically to the least busy queues, okay? That's kind of the gist of it, okay? Let's see the chart. This is what the chart looks like, okay? Now, first of all, you can see this is P99. This is not average. That's P99. You can see that, yes, there are occasional spikes here at P99 for, let's say, about 4 to 5 seconds, right? And this is where the system is rebalancing itself, right? But you can see that at P99, most of the tenants are still pretty low, well below 1 second latency. So yes, some tenants, right, are affected, and it might take several seconds for them to rebalance to the queue that is not affected, but this is happening automatically. This system is running for what, like more than 10 minutes here. You don't see those spikes to 2 minutes or 3 minutes, or worst case scenario here is a little bit above 5 seconds at P99 for a single tenant, okay? So the system is dynamically rebalancing itself all the time. Every time that scheduler runs, right, it gets the data, right, and updates my database.
And that's in a way an async scheduler as well. That needs to run every few minutes. If you had some other process that can poll more regularly, you've got even less of a possibility for contention.
Yeah, that is correct.
And in fact, Mika had it sort of succinctly done. I like that. Thanks, Mika. I was thinking of this like the express lane at the grocery store for people with 15 items or less. You can categorize jobs based on some time who go to a certain dedicated capacity. And in fact, this is what you're doing in the grocery queue, because you are often, maybe it's a single line or multiple lines, but you're often scanning the lines to go, that's the one I'm going to go into. Or, your passport control, that kind of thing. You're scanning the lines going, which is the least one, which is the most likely one that I'm going to get through quicker, trying to spot the families or the people who are going to give you trouble there in the queue ahead.
Yeah. And just like, I think there was like also one sentence, last 2 words was like around dedicated capacity. So even like after this, like again, you are at this scale, you will still hit into those probabilities, even though are like very less to happen. But again, when you run at that scale, so one of the thing is like you can know like this customer is like, or this specific SKU is going to be hotter. You can always assign them a dedicated queue, so they are not actually impacting other customers when you know. So like you need to have that mechanism where you sideline a customer. I think exactly what like Mikhail, sorry, I forgot his name, he was talking about. So you do to get into that, like where you sideline a customer so that like you are not impacting whole set of customers. And then what Anton was saying, that the P90 drastically reduces and gets closer to P90 in that case.
So yeah, in your blog post, which I will share the link again. So this is what you sort of basically explaining is that how Lambda in its async process is using SQS queues under the hood, and how you can use all of these shuffle sharding techniques to make sure that if somebody sends a massive payload through, other customers are not affected. And also, advanced things that I suppose we can look at our Lambda fleet and then go, oh, if we've got one particular customer which we maybe know is going to be doing a whole bunch of kind of stuff at a particular time, is then allocate them 1 queue or whatever, 10 queues. This is SQS. You just dynamically create queues, use it for whatever time, don't need it anymore, and then shut it down. I didn't mean to shut down Anton. I think he's just dropped off by mistake, but hopefully he'll pop back.
Got into busy partition.
Yeah, exactly. I think he's testing himself in the live stream as well. And just while we are talking about that, before we sort of wrap up, because this is super useful. The complexity is amazing, but also the simplicity is impressive. Sorry, we were thinking you jumped on a hot shard, Anton, and we're just
we have to bounce you.
So just before we sort of close, I just also wanted to say, and Anton, I'll get back to you. Is like Peter Smith. Peter, thanks for dropping this. The Amazon Builders Library has this article about shuffle sharding, and not just this article, but the Amazon Builders Library is literally the cleverest people at AWS are putting together these articles of how we run stuff at scale and sharing it out. And they're really well written. They're very accessible. It's not some sort of complicated mathematics mumbo jumbo. Really well done. So yeah, thanks, Peter, for prompting to put that link up.
Yeah. And like one of my favorite parts, right? We've talked about those different techniques, right? Lambda does it for you, right? So if you're using Lambda for asynchronous invocations, that's all done for you. You don't need to do anything. That's what you're getting out of the box. But if you want to implement it in your own systems, right? This is, one of the ways you can actually, reduce the blast radius, right? With three very different techniques.
Cool, excellent. So yeah, let me. I think I did put up that blog again, but if not, and I suppose 2 parts of this. When you're using a serverless approach, you don't really need to care because this is all happening behind the scenes. And then it's not just Lambda. Whether you're using DynamoDB or you're using EventBridge or you're using, the new maybe distributed SQL, which is being worked on at the moment. I mean, this is all stuff behind the scenes where the serverless services are taking on this hard job of resilience for you, and trying to sort out some of the noisy neighbor problems. But if you've got your own application that needs to get up to high scale, these are some great tips and tricks to be able to put it together. Well, Anton and Rajesh, I really appreciate your time. The blog was fantastic. When it came out, I looked at it and thought, I love getting into the weeds of Lambda. So it's super cool that you were able to put that together and come and explain it nicely and visually on Serverless Office Hours. So thank you very much.
Absolutely.
Thanks. Yeah, thanks for having us.
Excellent. And we'll be back same time, same place next week. It is also AWS Summit season. I was going to mention that in the beginning. It's the London Summit tomorrow. I know Stockholm's coming up, Dubai's coming up. What else is coming up? Poland is next week as well. So it's sort of in the European time zone for European people. Free, loads of technical sessions happening at the London Summit, at all the summits. Of course, the London Summit as well, because I'll be there tomorrow. But so please sign up for those as well. It would be great to see you. And we'll be back same time, same place next week for some more serverless goodness. So thank you, everybody. See you next week. Bye-bye.